show you my screen. So can you see my screen? Yes or no?
Yes.
Right. So this is Spectrum. You see, we will be back soon. Why you can log in? I cannot log in. So weird. Okay, no worries. Right. So today we're going to continue our discussion on our tutorial question number 3. So this week, Tuesday and Thursday will be my slot. So I will finish the tutorial 1 discussion. And at the same time, if students have any questions related to our atomic spectroscopic techniques, then please ask the question so that we can discuss together in this tutorial session. And I will also continue with tutorial 2 discussion on amperometric and voltammetric analysis, electroanalytical techniques to do quantitative and qualitative measurement for analytical chemistry. And later on, I will tell you something about our final exam. So before we can proceed to all these things and complete it by this 2-hour session today and Thursday, let us continue with our tutorial 1. We have another 3 more questions to discuss. So let us discuss this question number 4 now. The intensity of line for atomic cesium is much lower in a natural gas flame, which operates at 1800 degrees Celsius than in a hydrogen-oxygen flame, whose temperature is 2700 degrees Celsius. Ask the students to explain, because this is uh, uh, how fundamental and also some critical thinking for students to understand why we can observe this situation. So before this, I would like to know whether students, do you understand the concept for this atomic spectroscopic between AAS, AES, and AFS? Of course, obviously, this question is not related to AFS because there's no signal, fluorescence signal. So either it is AS or AES. So I would like to know the opinion from the students, see whether you understand this question. First, before we answer the question, we have to understand the question first. So this is what I always emphasize, and this is important for your final exam. I will talk more about our final exam later on. Once we finish discussion on our tutorial 1 and tutorial 2 answers discussion. So now I would like to ask someone to help me to go through together with this tutorial answer discussion. So I would like to invite Ang Chang Kai. Ang Chang Kai, please switch on your microphone and also, if possible, video, because I never seen all of you. I only see myself. So Ang, if you are convenient, please on your camera as well. Can you tell us, this question is about, we are talking about which technique? Which technique? Ang? Yeah, would you mind to switch on your camera? Right, so it is about what technique? This question is about which technique?
It was
So
yes.
AES, yes, good student. Why you say it is AES? Why you say it is AES? What keywords that to tell you that
is higher. Temperature is too high.
Temperature is too high? Temperature is too high? 1,800 and 2,700.
And of course the flame used.
Flame in AAS also use flame, man. In AAS also use flame. Why you say this question is about AES? AES we also use flame as atomizer, right? Why this question is not AAS but AES?
Intensity of the line.
Yes, good answer. Because of this is intensity of line. This intensity is what type of intensity? Is it an absorption intensity or emission intensity?
Emissions.
Emission intensity. So the keywords here is the comparison between temperature, right? So why I asked this question is I would like you to know that in AAS, the temperature of the flame, it has two functions. If it is in AAS, the flame is only act as atomizer, right? So if it is in AES, it is act as an energy source where there are two important processes, atomization and excitation. Okay, if you look carefully, this question is about the comparison of the intensity of the lines. It didn't mention clearly whether it is an emission line or absorption line, but we know that it has to be an emission line. Why it has to be an emission line? Because it's comparison between the flame temperature. In AAS, the flame temperature, it doesn't matter. It won't cause any impact towards the signal of our detection, the intensity of the absorption signal, because the intensity of the absorption signal is due to the excitation is due to the light source, but not in the case of AES. In AES, the flame temperature is highly affect or have impact, strong impact towards the intensity, the population of the excited atom from the ground state to the excited state, right? So that is important. So we know that this question is related to AES because it has a comparison between the flame temperature, the energy source temperature. And we know that for this case, this cesium, this is the target analyte that we want to determine, right? Qualitatively and quantitatively. At low temperature, we cannot get intense line. Means that the emission line, the intensity is proportional to the concentration of our target analyte cesium, right? If we have low intensity, means that at low temperature, there is the excitation atomization process not effective, right? So if the temperature is high enough, right, to let the excitation happen from the not only the atomization but also the most importantly is the excitation, because in AES what we measure is the emission. How to get the emission is only after the atom from the ground state being excited to the excited state and relax to the ground state, then only it can emit emission, right? Emission radiation in terms of photon, electromagnetic radiation. This is what we measure the signal, right? So in quantitative measurement, it is relates to how much, not only how much the concentration of the analyte, and also the most important thing is how much the analyte can be atomized and get excited. Okay, so this is the explanation to this question. First, we must know is meant for which technique. Okay, so here I give you an example of the model answer. The excitation is relates to the energy gap, right? The energy gap. So if we go back to our lecture notes, our pre-recorded lectures in our first chapter, so this is the important topic that you have to understand about this Boltzmann distribution, how temperature will affect the atomic spectroscopy. And this atomic spectroscopy is only focusing on AES, atomic emission. Because for AAS and AFS, the excitation, as I said, and also emphasized many times, many times, is due to the light source, punca cahaya, that cause the excitation. Why I always during this tutorial session, I always mention this many times, emphasize on the concept, because ideally is all our students, we have 34 students, we're supposed to have 34 students, as you can see here. We only have 19 students. Deduct me, only 18 students joining. Deduct 2 because I'm doing presentation. Only 17 students. Another half of students didn't attend. This concept is extremely important because in the final exam, I will ask majority of the question is about the concept. You have to get the concept right. I only have one question, 1 to 2 question is about the critical thinking question. For those students who really can critically think how to answer those questions. The rest of the questions are all fundamental questions. So you have to attend this tutorial session to recall back, to catch back what you have missed in the pre-recorded lecture. Have to make sure that the fundamental concept is correct, right? So for this atom from the ground state to be excited, it need to absorb energy. And where does this energy comes from? If it is in AES, the energy comes from the energy source. For this case, the question is flame, right? So the flame is the energy is too low. This atom, the target analyte, it cannot excite from the ground state to the excited state. So it must have sufficient energy. You see, there is a delta E. Delta energy means there is a gap of energy that these atoms, after atomization, they have to get this enough energy to get excited. They must get excited first before they can relax to the ground state and emit emission, radiation, which is what we measure in atomic emission spectroscopy. Okay, so for this question, the energy needed to promote a ground state, we know that, okay, for cesium is group 1 element. Cesium group 1. Even though that cesium, it has low energy for the atomization, for the excitation, but it needs certain amount of energy to get excited, right? So group 1, it has what orbital? Only orbital S, orbital D, right? If it comes to transition, it has orbital S, orbital P, or orbital D, SPD, right? So for this cesium, from orbital S, the electron, it needs to get excited to orbital P, right? It needs enough energy, right? So for this 1800, not enough. Only little bit of atom can get excited because not enough energy, right? So if let's say we increase the energy, right, from this natural gas low temperature to high temperature, we are able to excite all those atomized atoms and get them excited from the ground state to the excited state. When they relax to the ground state, they will emit high intensity of emission line. Okay, so state so high that only fraction of the cesium atoms are excited at low temperature of, if we use natural gas flame. At a higher temperature of this hydrogen and oxygen flame, a much larger fraction of atom is excited and more intense cesium emission line will get, we will get results. So this question is very simple question, straightforward, just that students must have a little bit of critical thinking in order to get this question correct. So far, students, do you have any question you want to ask about this question? Do you understand the concept? You have question? If you have question, please ask, yeah? So if no, then we proceed to our next question. Okay, next question is, why is atomic emission more sensitive to flame instability as compared to AAS and AFS? Okay, very simple. In AAS and also in AFS, as I said, mentioned, and I already mentioned, emphasized many times, the excitation is due to the light source. Okay, due to the light source. Only for the AES, the atomization and excitation is strongly affected by the temperature of the flame. It's not only by the temperature of the flame, it is also affected. If we go back to this lecture notes, I want to draw your attention because it's not only the main factor which affect the population of the excited atoms is due to the flame, right? But another factors, a few other factors that would also affect this population of those excited population. So if we go to AES, let's move on to AES. So we know that in order to solve the issues of this unstable temperature of the energy source, especially in flame, In inductively coupled plasma, we still can control as long as we can control the this coil, the copper coil, the generator, the plasma generator, the temperature, we can have a better control. But for flame, it is hard for us to control the temperature of the flame, right? So that's why we have to use the internal standard. We will talk about this in question number 6 about the internal standard. But now I want to let you know that not only the temperature will affect the population of the excited atom, but also this one, another thing is the signal will vary. This what we can get it from the second last slide in our AES. When we talk about our pre-recorded lecture, our AES, we need internal standard to solve the problem. Because of this, the signal will vary from time to time due to what? Due to the unstable temperature, and also due to what? Another two other reason is because of the fluctuation of the gas flow rate as well as the aspiration rate. So three important factors that will cause the number of the population at the excited state in AES. Only in AES will get this impact. In AAS and AFS, no. First is the fluctuation, unstable temperature. Second is the fluctuation of gas flow rate and also the expiration rate. Okay, so if you still remember, in AES, we want to introduce to the sample. In AES, atomic emission, this is ICP. We use this. Use this. When we want to introduce the sample into this AES, with light source is AES, without light source is AES. We need to have this go through the nebulizer and also the spray chamber. Okay, so when the sample in the liquid form, in aqueous form, being introduced into this system, the flame, the energy source for the atomization and also the excitation, it has to go through this dissolution evaporation process, right? And how to make this process more efficient? We have to introduce the sample through the nebulizer and make it into a fine droplets so that the evaporation dissolution can be done more effectively. So this is related to the flow rate. How fast you introduce the sample. This all can be controlled by the computer. The software can control. And how fast these samples in aqueous, in liquid form, being aspirated to become a fine droplets and introduced into the energy source, into the flame, and get atomized and evaporized, atomized and excited. So not only this temperature will affect the population of the excited state, starting from the sample introduction, we already have to count this, the aspiration rate, the flow rate of the sample introduction until it reached the flame. So all this will have impact on the population of the excited atoms in AES. Right, so this is the given model answer. The population of the excited atoms from which the emission arises. Emission arises means how to get the emission line, emission intensity. First thing is you must get the atoms. Atomize, atoms already said atoms means the samples already atomized. To get excited first, is very sensitive to the flame temperature. This is undoubtedly because I already told you that as what we mentioned here, the effect, the Boltzmann distribution, all about the temperature and other conditions like the aspiration rate, the flow rate, as we discussed here. So all the answers you can find it from your lecture notes, including the final exam. So gas flow rate and aspiration rate. Okay, so the population of the ground state atoms. So this is a comparison because it asks why for AS and AFS is not sensitive to this flame instability? You have to answer that question. You don't only answer the part for the AES. If you only answer the part for AES, you won't get full mark. Same thing for the final exam. So you have to answer the part for AAS and AFS. The population of the ground state atoms from which absorption and also fluorescence originate is not as sensitive to this condition. Either this flame instability, the aspiration rate, the gas flow rate. No, it's not sensitive since it is much larger fraction of the total population, because what we want to measure for AAS and AFS is the ground state atom, right? Once the radiation, the electromagnetic radiation from the light source shine upon this ground state atom, then they get absorbed. So before they get absorbed, what is the thing that is important? The ground state neutral atom, for AAS and AFS. That population is the important. When it get excited, this is the signal that we measure. The absorption signal, right? But for AFS, it's not. AFS, what we measure is the, when it get excited, then it relax, emit fluorescence. But before it get excited, the population, the neutral atom at the ground state is the most important thing, because there is a light source to get it excited. So have to be very careful and have to understand all this concept between AES, AAS, and AFS. AS, AFS, and AES. This one only highly affected by the temperature, the gas flow, the aspiration rate. Not for these two, because the excitation and also the population at the ground state is, for the excitation is due to the light source. Okay, so if you answer, you see all my answer, very short, right? Short answer and simple, straightforward. No need to write an essay, a long essay to get full marks for your final exam. Now I am telling you the skill, the strategy to answer question in order to get full marks for your final exam. Final exam question, very simple, but you have to be very careful. Have to answer all question for all, give the answer for all question, because sometimes the question, it seems easy, but maybe you only answer the first part, but you forgot the second part, then you won't get full marks for it. It's a waste if you don't do that. So now we move on to the last question for tutorial 1. So I hear some voice. Any students you want to ask question?
Yeah, I have a question regarding the AF and AFS side. I wonder why the flow rate and aspiration rate does not affect the population of neutral atoms. If your flow rate fluctuated, the population of atoms inside the chamber will be affected, right? For
Okay,
the AFS.
as I said just now, for this AES, the most impactful for the population of the excited is due to the temperature, right? Only small impact comes from what? Comes from the flow rate and also the aspiration rate, right? Only the small impact, because we cannot only say only temperature will affect the AES, right? The flow rate and also the what is that called, the aspiration rate, yes, definitely it will affect, but it's a very minor impact, right? So now go back to AES. Same thing happens. The flow rate and also the aspiration rate, it will affect, but it's not as high impact as the light source from the electromagnetic radiation from the light source. If we go back to our lecture notes, okay, in AS, our lecture notes. So if we notice that, still remember our AS, right? So we have not this one. We have to go back to our first lecture, which I introduced to you about this, the laminar flow and also the turbulent burner. So this will give us different flow rate, turbulent flow, burner, and also the another thing is the laminar flow. So all this, if we use this type of burner, right, for the atomic vapor, if we get to know that, oh, this is not a good flow rate, then we can change this one. But that is not the major impact, right, towards the population of this ground state neutral atom in AAS. How to get this population of this neutral ground state atom to get excited? It all comes from the light source. That is the most important thing. This flow rate is only will help us on the atomization, right? Atomization, because this sample introduction, when it introduced to this atomizer, is only have some impact on the atomization. The excitation in AAS is not about the aspiration rate, fully about the aspiration or the flow rate. Aspiration and flow rate is related to the atomization. Okay, so the excitation for the ground state is really totally come from the light source. Is it okay, Leon?
Okay. You means the efficiency of atomization have no impact.
It will have related to the flow rate and also the aspiration in the process of atomization in AAS. Okay, the population of the neutral ground state to get excited is not due to this aspiration and also the flow rate, because in AAS, aspiration and flow rate is only related to atomization. The excitation comes solely from the light source. But in AES, because we don't have the light source, the atomization and also the excitation comes from the flame, the energy source. So that's why flame, it has two functions, atomization and excitation. The flow rate and also the aspiration, which is related to atomization, will take into consideration. Okay, Leon, understood?
Okay.
Okay,
Great.
good question. Good question. Have critical thinking. I like this. So the rest of you, please, I encourage you, right, so that we can know more, understand more about the concept. So now we move on to this question number 6, the final question. Cannot show you the answer first. Okay, so now, what is the purpose of an internal standard in flame emission methods? So as we discussed, we know that in flame, right, flame AES, flame is very unstable, right, as compared to inductively coupled plasma. Flame unstable, so the temperature is unstable. So as we learn from this Boltzmann distribution, what we learned, let me go to the Boltzmann distribution. So a small change, only 4 Kelvin change, 4 Kelvin, then it will give us only 10 Kelvin, 10 Kelvin, it will give us 4% of 4% of difference in the excited population, 4%. So 4% is in terms of this ground state and excited state, 4% is considered huge. It will give us if the signal is due to the temperature change, it will give us unreliable signal. And how to solve this problem? So we go to this AES lecture. That is, we have to use the internal standard. Okay, in AAS, AFS, we do not use this internal standard. Only in AES, we are required to use this internal standard. So why we have to use this internal standard? Because when we plot, I have to draw something for you. Let me, okay, tutorial. Sorry, I don't want to open this. I want to open this so that I can draw. Okay, so this is the question, last question, right? So I want to do some drawing. Okay, so this is our calibration plot. For us to do quantitative measurement, we must plot a calibration plot. Let's say we want to detect sodium, simple target analyte, sodium, right? So we know that sodium is group 1 element, right? Group 1 element. So it is easy to get ionized. If the temperature is high, then it will get ionized. So we use potassium to suppress the ionization of sodium. So for this case, if we want to detect sodium, which is the best element to be used as the internal standard for sodium detection? We want to detect sodium. Sodium easy to get ionized, right? So we use potassium to suppress the ionization of sodium, right? So if we want to detect sodium in our sample solution, which are the elements, which is the elements that is good to be used as the internal standard? Any students?
Lithium.
Lithium. Lyman answered, right? Good student. Lithium. Okay, correct. The answer is correct. We can use lithium, right? So if we want to perform quantitative measurement, we need to do a calibration plot, right? So I have 1, 2, 3, 4, 5. 1 ppm, 2 ppm, let's say 3 ppm, 4 ppm, and 5 ppm, right? So when the concentration increase, right? So if let's say the temperature is good enough, right, to let the ground state neutral atom get excited to the excited state. So when it's relaxed to the ground state, it emits radiation. So the intensity will be proportional to the intensity, this intensity of emission line, it is proportional to the concentration of this target analyte, the sodium. So we use lithium as the internal standard, right? So it's supposed to be like that, right? So this is ideal situation, okay? So this is what we measure, the intensity, intensity of the emission line. Okay, intensity. So this, okay, right. So if let's say the flame temperature is unstable, right? We need to use an internal standard. If it is unstable, so there's a change, small change during the process of our measurement, a fluctuation of the flame, right? So there is a small 10 Kelvin. It gives us 4% of population change, 4%. So if that's the case, we are not able to get a proper calibration plot because this intensity will be fluctuated accordingly if there is any unstable flame temperature, right? So means that this calibration is not reliable, not accurate. So how to solve this? The answer is to use an internal standard. So now we have to explain why using an internal standard will help us to get a more reliable calibration plot. More reliable calibration plot. Because this calibration plot, if we only base on this intensity measurement, intensity, the signal is the emission intensity. So we call this as an absolute. So the intensity is based on the concentration. Intensity increase. Of course, we know that intensity will increase if the concentration of our target analyte increase, right? However, this intensity that we measure is an absolute intensity. Absolute intensity is unreliable because this intensity will change anytime if the temperature of the flame is unstable, right? So it means that this calibration plot is unreliable and we cannot use it to perform quantitative measurement to detect or to quantify the concentration of an unknown sample. So how to solve this problem is we use internal standard. So we need to explain how to use an internal standard so that we can build a reliable calibration plot. So any student can help me to explain why with the addition of this internal standard, in our case detection of sodium, we use lithium as the internal standard, and how to make the system, the calibration plot more reliable. I need a student to help us to answer this question. May I ask Muhammad Sabri? Muhammad Sabri, can you help us? Mm.
Because
Mm,
when we use internal standard, we will improve the precision. Thus,
mm.
when there is any fluctuation occur, we will know the roots of it because all of the element will affected similarly.
Yes, yes. If let's say Muhammad Sabri, congratulations, you answered it correctly. Part of the answer is correct. So means that okay, let's say we want to know um, if there is any fluctuation in flame temperature or in any aspiration rate or what else the flow rate, gas flow rate, right? So the impact will be the same not only towards the sodium, the target analyte sodium, right? But it also will towards the lithium, right? So that's why we must have this lithium because if temperature increase, it will have impact to sodium and also to lithium. If temperature decrease, it will have the same impact towards sodium and lithium. Right. The first part of the answer is correct. So it has two impact. So how can we relate this sodium and lithium? How can we relate this sodium and lithium? Because we know that the impact of all these changes are temperature change, gas flow change, and also what else? Gas flow change and also the aspiration rate change. So how to relate to these two? It will have impact, right? So how can we link between these two? The target and also the internal standard. Link them together so that whatever changes, we know that it's come from these changes, from this environment changes. I call it as environment because this is the impact from the environment, the flame temperature, the aspiration rate, and also the gas flow rate. It's not due to the change of intensity. It has to be due to the change of the concentration of the target analyte, isn't it? Right? But because of this environment change, it will cause us a change of signal, the emission, the intensity of the emission line. So I want to for sure the change of the intensity of the emission line is solely due to the change of the concentration of my target analyte, but not from the environment. I need a internal standard lithium. So how can I relate between this sodium and lithium? How can I make a relationship, right? I know that the environment change, it will affect my target analyte, sodium, and also will affect my internal standard lithium. But how can I link all this together so that I can plot a reliable calibration plot in order to perform a quantitative measurement, accurate quantitative measurement? Thank you, Muhammad. I would like to call upon another student to help me to answer my second part of question. I would like to invite Isyen, Isyen Amani. Isyen, Isyen, are you online? Huh? Isyen, Isyen? Okay, no worries. Maybe Isyen not convenient to answer. How about Lee? Lee Bunhong? Lee Bunhong?
Yes, doctor.
Yes,
I'm
please
here.
help us. How to make these things relate
Mm,
one to another so that I can solve the problem from this environment. I want to be sure the signal change intensity is my signal. My signal intensity of the emission line is solely comes from the change of the concentration of my target analyte with regards to this internal standard. How can I do that? So that the environment change, I don't care. Temperature increase, gas flow reduce, aspiration rate reduce, because it will have the same impact to my target analyte and also to my internal standard. I just want that this environment will get rid and have no issue at all for my quantitative measurement in my calibration plot. How to do that?
the lithium can added to the standard.
Lithium is the standard. Is
Yeah,
the internal standard.
is added to the sample,
Yes,
and
it
hence
will.
the lithium and the sodium is the same chemically similar, and the
Mm,
wavelength is not too different. So we can ensure that the intensity can totally depends on the concentration of the target analyte.
Yes, the answer is what you mentioned is the fact. Is what have been mentioned here is the requirement for the good internal standard, but it's not answering the question. No worries, I will guide you to answer the question. Okay, so how can we know that all the criteria needed for this internal standard. No worries, Lee. This is a discussion process. We learn together. This is a critical question. How can we, Lee? How can we incorporate this lithium into our calibration plot? How can we incorporate this lithium into our calibration plot so that it will give us a reliable quantitative measurement? When we talk about quantitative measurement, it's about the calibration part. How can we incorporate this lithium? We know all the criteria, but how can we incorporate this? Can we incorporate this in the x-axis or in the y-axis?
Using ratio.
Huh? You answer correctly. Be confident. Lee, good student, huh? Ratio
It's
of
not
what?
my answer.
No worries. Pretend that this is your answer. Ratio of what? Ratio of what?
Ratio of the intensity of the analyte.
Yes, analyte and also the internal standard. Okay, good student, good student Lee. Actually, all of you are good students. Just that some of you may be shy to answer, but you have to believe you are a good student. So this is important, especially when you come to your final exam. So now we move on. Intensity. If let's say we only measure the absolute intensity of the sodium, right? So this intensity is unreliable because it will get affected by the change of the environment, the flame, the aspiration rate, the gas flow rate. Okay. So if let's say we want to solve the problem, we must use an internal standard, the lithium. So now what we measure here in the y-axis is no longer the absolute intensity of our target analyte sodium, but we get a ratio intensity of the emission line of this sodium versus the lithium. We get a ratio. Okay, so this will take into consideration whether any changes made by the environment, the flame temperature, the aspiration rate, the gas flow rate, it won't have much effect, right? Because we already taken into consideration the ratio intensity between our target analyte and also the internal standard. So what is the relationship between this relation between the sodium and the internal? The intensity ratio, it is a constant. It should be a constant, right? It should be a constant. How to make this ratio intensity a constant? You must get the concentration of lithium fixed at one concentration. Okay, let's say the ratio of intensity, let's say ideally the intensity is 1 for 1 ppm. For lithium, if it is 2, is 2 ppm. Intensity is 3, is 3 ppm. 4 is 4 ppm. 5 is 5 ppm, right? So for lithium, we have the internal standard. We must fix the concentration of the internal standard. Either we spike this internal standard into our standard or into our unknown sample. We have to spike the internal standard into the standards. This is what we call standard. Standard means we know the concentration of our target analyte. We call it as standard. Or into an unknown. Unknown means you don't know the concentration of your target, but you have to spike the internal standard with a fixed concentration, non-concentration. Let's say we spike 1 ppm. So this concentration in a calibration plot, it will change, right? But this concentration is fixed. So the intensity for this lithium, it should be, let's say it's 1:1, right? 1 ppm is to 1 intensity of emission, right? So let's say this lithium we use 1 ppm, so it should get one signal. The intensity is 1. So the ratio intensity between the target and the light. So now instead of getting this absolute intensity, we get the ratio intensity for the target analyte versus the intensity of the internal standard. So if you have 1 ppm of sodium, you have 1 ppm of this lithium internal standard, 1. So you should, the ratio constant 1 at one concentration, this particular concentration 1 ppm, the ratio will be 1. So the ratio, if let's say we change the concentration, increase the concentration of sodium to 2, this is 1, 2 lithium, we have to fix the concentration, right? 1. So the ratio intensity constant, it is 2, right? So this constant, either it is 1, 2, and so on, 3 ppm. When it reach 3 ppm, this one still remain as lithium as 1 ppm, the intensity also 1. So this 3 ppm, the intensity is 3. Let's say, so the ratio constant is 3. So all this constant, the ratio intensity constant between the target analyte and also the internal standard, it is a constant. This constant, the ratio intensity. So this constant, already say constant. Constant means it won't change. So if there is any fluctuation, any environmental change from this flame temperature aspiration rate or this gas flow rate, it won't change this. It won't change this. That is why we have to use the internal standard. Okay? So can this constant change? Can this constant change? So the environmental change, no problem. So when you plot this graph, right, this calibration plot, right, instead of using absolute intensity, emission intensity for your target analyte sodium, you cannot use this. You have to plot this graph using the ratio intensity. Signal is ratio intensity of target analyte versus the internal standard. Then this graph will take into consideration if there is any change in environment. It won't affect, right? Because this, it has to be a constant. It depends on which concentration. The ratio must be a constant. This is the purpose why we want to use the internal standard. Okay, so now I want to test whether you understand or not what my explanation is. Now I say the ratio constant is the ratio, it is a constant, right? It won't change, even though that if there's any changes or fluctuation from the environment. Would the ratio constant change from time to time? What condition will make the ratio constant, ratio intensity change? What situation will make the ratio intensity between the target analyte and also the internal standard change? It's a simple question, just to test whether you understand my explanation or not. I need Muhammad Husni to help us to answer. Muhammad Husni, can you help us to answer this question? If we do the plotting, calibration plot, instead of using absolute intensity from the target analyte sodium, we change it into this y-axis. What we measure is the ratio emission intensity between the target analyte and also the internal standard. The internal standard concentration should be fixed, either in standards or in unknown sample, right? So because of this ratio intensity, it is a constant. It won't change. For 1 ppm, it should be 1. For 2 ppm, concentration of our target analyte, it should be 2. The constant should be 2. For 3 ppm, it should be 3. For example, if let's say at 1 ppm, you get the intensity is 1, 2, 3, 4. Accordingly, right? So in what kind of situation this ratio intensity constant will be changed? A simple question. Muhammad Zulhusni, can you help us to answer this question? Quick. Muhammad cannot answer? Not convenient? No worries. Maybe you can ask Siti? Siti, can you help us to answer? Siti also cannot. Can we ask Nur Ain Nazira? Yeah, Nur Ain. Yeah. In what kind of situation, right? Because we know that in all kind of situation, if there is a fluctuation of temperature, we focus on fluctuation of temperature, right? It won't change the ratio intensity of our target analyte towards the internal standard. The constant, I already said constant, right? It won't change. We don't care. Temperature high, temperature low, it won't change the constant intensity, ratio intensity, because it is a constant. At 1 ppm, it should be 1. At 2 ppm, it should be 2. At 3 ppm, it should be 3. This is the constant. In what kind of situation it will change? It will change the ratio intensity, the constant of the ratio intensity. At what kind of situation? Nur Ain? Yeah, Nur Ain, help us to answer this question. This is to test whether you understand my explanation or not. You can think critically. Nur Ain? Oh, no answer? Nur Ain cannot answer. Okay, let me invite Khor Lyman.
Yes, doctor. I think is it the concentrations of the standard solution, the sodium concentration?
Yes, good student. You gave the correct answer. Absolutely correct. How to change the ratio of this intensity? It's only when we change the concentration of our target analyte. You see, I changed the concentration from 1 ppm to 2 ppm to 3 ppm. Then the constant will be changed. Okay, so what information we get from this study? This study tells us that in order not to be affected by the environment condition, we must have, instead of getting this intensity, absolute intensity for our target analyte, we should go for ratio intensity. Because this ratio intensity, it is a constant. It won't change even though that there's any change from the environment, right? This ratio intensity is only changed when we change the concentration of our target analyte from 1 to 2, 2 to 3. So this is what we want when we want to do quantitative measurement. What we want to do is, if there is a change in the concentration of our target analyte, our signal will be changed, right? So this is what we get. If we incorporate or include the intensity of the internal standard into our calibration plot. Okay, so it's very simple concept, just that we need to do a little bit of critical thinking, then we can answer well for this question. I know all of you get this answer correctly, maybe because of from the internet or from what, but we have to know the basic concept to understand. Before you able to provide this copy paste from the internet from your senior, no worries, you can do that, but you make sure you understood the basic concept. When an internal standard is used, the ratio of the intensity of the analyte means our target analyte, to that of the internal standard. Analyte is sodium, internal standard is lithium. The ratio of the intensity, we have to plot to plot the ratio intensity, versus as a function of the concentration of the analyte as a function. This is a proper language we use. Most of the time we say this y versus x. But when we write in a scientific report, scientific way, we have to say as a function of concentration of the target analyte. So if let's say the internal standard and the analysis species, the analyte is influenced in the very same way by variation in the expiration rate lah, the gas flow rate lah, the temperature of the source, the energy source. And if the internal standard is present at the same concentration means that you have to fix the concentration of the internal standard in the calibration standard and also the unknown. When you spike the internal standard, you have to spike the fixed concentration. Whatever concentration you can choose, 1 ppm, 0.1 ppm, 0.3 ppm, no worries, it's up to you. But the concentration you have to fix for the internal standard. You spike into the calibration standard. This is your calibration standard, either in 1 ppm, 2 ppm, 3 or 4 or 5. This is your calibration standard, and also into your unknown sample. So the intensity signal ratio, intensity is more appropriate, the intensity of your emission line or the signal of your emission line. But this is not emission line for your target analyte, but it is the air ratio between your target analyte and also the intensity, ratio of intensity between your target analyte and also the internal standard at a given concentration, either it is 1 ppm, 2 ppm, 1 ppm, 2 ppm, 3 ppm, the ratio, it is a constant and it should be independent of these variables. Variables is what variables? Means the environment change, the temperature change, the aspiration change, the gas flow change. It change, no worries, because it won't affect the constant, the ratio intensity. What would affect the ratio intensity change is only when we change the concentration of the target analyte. And this is what we want. We want the signal that we measure change is due to the change of the concentration of the target analyte, but not from the impact from the environment. Okay, so very simple concept, just that you need to understand. Okay, so now it's 8:58. We cannot move on to the tutorial answer discussion for question tutorial 2. So next week we will discuss about the answer for tutorial 2. Not next week, this Thursday. Tutorial 2, and also I will give you a short presentation for our final exam. Tell you how to answer, and I'll give you some hints on the final exam question. Okay, so remember to take your e-attendance. If you cannot log into Spectrum, no worries. You log into you join this Microsoft Team. Microsoft Team will produce this I show you this is our previous meeting, so it will produce the attendance, but you have to join this meeting, then only you have your attendance. I will consider this attendance as well. If you, let's say you forgot to sign the e-attendance on eSpectrum. Okay, so that's all. You have any question? If you do, you may WhatsApp me, email me. I will try my best to answer your question. And please remember to click leave, because sometimes it takes a long time for me to post the recording on the eSpectrum because of student forgot to click this leave. And if you don't leave, if all the participants not leaving this meeting room, then the recorded video will not be generated. Okay, so 8:59. So that's all for today's meeting. I shall meet you again on Thursday, this Thursday at 8 a.m. So Leon, you have anything to say?
No, I just want to remind you, you can stop the recording before you leave.
Oh, I can stop. Right, I don't want because okay, I can do that as well. So stop the recording. So I think that's all.